Welcome to our discussion of content for SCP-140. Today we'll discuss some of the materials in chapters 3, 5, and 6 of the OpenStax Astronomy 2nd edition. I'll be showing you some of the images in the textbook and putting my particular spin on what I think about these ideas and these concepts. Hopefully, many of these discussions will help you in solving some of the problems on the homework and in future work that you're doing in the class. We start off with an image of the International Space Station. Many times when students first come into this class, they have some preconceived notions about the way things work in space. For example, many students believe that when a rocket launches into space, the reason that the astronauts that are on board the rocket experience weightlessness is because they've somehow escaped the gravitational pull of the Earth. This really isn't the case at all. And in fact, it's illustrated quite nicely in this image of the International Space Station, which is right now the largest human-made object that is orbiting the Earth. And currently there are astronauts on board, living and working. And of course, they're experiencing weightlessness. But if you actually measure the amount of gravity that they're experiencing, it's almost the same, very, very slightly slower than the gravity we experience here on the surface. That's because the International Space Station isn't that much further away from the center of the Earth, from where most of the gravity we experience is generated, than we are. It's a mere 100 kilometers above our heads when it's directly at zenith. That's not much further from the center of the Earth than we are. We are at about 6,300 kilometers. They're at about 6,400 kilometers. And if you run the calculations, you find that the force of gravity that they would be experiencing is basically the same as us. So why do they experience weightlessness? We'll try to answer that in a bit here. But basically, the idea is that they are not escaping from the gravitational pull of the Earth. There is another effect which causes it to appear as though they have escaped from gravity, but in fact, something else is going on. Now, the people that were working first on these problems of gravity and what motion in space looks like and means go back many, many generations to the dawn of history, perhaps. But the calculations that we will be doing in this class and the work that was done carefully to measure the motion of objects in the sky that are acting under the influence of gravity were accomplished by a few people working about 400 years ago. And here are two of them. On the left is Tycho Brahe, who was an eccentric and extremely rich aristocrat in Europe who got obsessed with the sky and watched it night after night after night for years and kept detailed notes that were so detailed and so accurate that they were enabled other people that came after him to really figure out exactly how things were moving precisely through the sky. And this was important for coming up with the right model for how objects moved around our solar system, around the Earth, and eventually under the influence of gravity. Now, Tycho Brahe never really came up with the correct answer for these motions. That would be left to the person on the right, Johannes Kepler, who took Tycho Brahe's data and then carefully figured out what paths the planets were taking around the sun, and also confirmed that the Earth was just another one of these planets. Up until that point, most people were convinced that the Earth was the center of the universe. This had been the way the Greeks had described things. This is the way that most people around the planet had been describing things. And indeed, when we were doing our own observations, we sort of assumed this as well. But there are tiny little variations in the motions of the planets that show that this can't quite be the case. And Kepler was able to look at these, do some careful calculations, and come up with what the correct shapes and correct motions and speeds of the planets around the sun were. and indeed the correct motion and speed of the moon around our own Earth. In fact, Kepler's work also explains how the International Space Station maintains its orbit around the Earth as well. What Kepler found was that all of the planets went around the sun in a shape called an ellipse. Now, if you haven't encountered the word ellipse before, here's a nice way of envisioning it. The shapes that you can make from a cone, slicing it in various ways, are called conic sections. And it happens under the influence of gravity that all the paths that are possible under the influence of gravity follow a conic section. Kepler just happened to notice that the planets follow a particular one, the ellipse. The ellipses that the planets follow are actually quite close to circles. You can look and see what the actual orbital paths of the planets are, and it's a little bit difficult to tell that they're not exactly circles, that they're actually a little bit flattened as ellipses. There are other types of orbital paths that can happen as well. There are parabolic paths and hyperbolic paths. These are paths that we wouldn't necessarily describe as orbits, because if there is an object on such a path under the influence of gravity, they'll actually escape and move away as far as possible, eventually, from the object that they are experiencing the gravitational attraction. But when Kepler was really investigating the motions of the planets, he had to be careful in describing exactly how ellipses worked. And this is an example of how you would make an ellipse. In order to make an ellipse, you put 2 points that are fixed. We call them the focal points of the ellipse. And then you attach a string around those 2 points and a writing instrument, and then trace out the path. That path that gets traced out is an elliptical path. And we can also define a size for the ellipse. And the normal way we define a size is we take the longest length across the ellipse, we call that the major axis, and we divide it in half. When we do that, we trace out something called the semi-major axis. And we often label that A. And in many cases, you'll see that labeled A. That happens to be the average distance between a planet and the sun. So for example, the Earth is an average distance away from the sun of 1 astronomical unit. Or we could say that the Earth's orbit has a semi-major axis that's 1 astronomical unit in size. An astronomical unit is going to become an important measurement in our exploration of astronomy. It's a really large distance. It's about 1.5 times 10 to the 8 kilometers. And you've explored it already if you've read through chapter 1, and even some of the other chapters mention it as well. We'll continue to use this unit as a handy measuring rod throughout our studies of the solar system, but also beyond. Another thing that Kepler discovered when he was examining the planets moving around the sun was that the planets seem to speed up when they get close to the sun and slow down when they're further away. And they do it in a very particular way. If you were to trace out the area that a planet would sweep, if there was a line that connected the planet to the sun, and incidentally, the sun is always at the focal point of one of the ellipse, then what you would see is that the planet sweeps out what they call equal areas and equal times. The effect of this is that the planet moves more quickly when it's closer to the sun and slower when it's further away. This makes some intuitive sense. When we describe gravity in a little bit more depth and detail, you'll actually get a sense for why this is. If we think of gravity as a well, and as you get further down into the well, you gain some sort of kinetic energy by exchanging it for something called potential energy, you end up moving more quickly at the bottom of the well. And then as you climb out, you lose some of that kinetic energy and you gain potential energy and you move more slowly. We'll examine that sort of concept a bit more in the future, but this is something that's deeply related to Kepler's exploration of why planets move more slowly when they're further away and more quickly when they're closer in. Moving on, the explanation for why planets were doing this wasn't really evident to Kepler. He didn't have an understanding of why that might be, and just kind of thought that this was just the motion that things in the heavens had. Isaac Newton is considered by many to be perhaps the most famous and perhaps most important scientist perhaps to have ever lived. What he first was able to do that no one else had figured out before was connect two phenomena that seemed very disconnected: the motion of the planets and the moon in the sky, and the motion of objects as they fell towards the earth. And what Isaac Newton realized was that those two motions were actually part of the same phenomenon. They were the same thing. And he could show how that was the case. We actually see this a lot when we start to examine some of the things that we observe in our day-to-day lives. It maybe was not as evident in Newton's time, but it is now. For example, Newton made some observations about how motion happens. Observations about how force is associated with not just motion by itself, but motion that speeds up or slows down or changes direction. We call that an acceleration. Newton also noticed that objects that were in motion tended to stay in motion, and objects that were not in motion tended to not be in motion unless a force was acted on them. This is called inertia, or Newton's first law. Newton's second law of motion is called force is equal to mass times acceleration. At least that's the simplest way to describe it, sometimes called the second most famous equation in physics. We won't use it too often in this class, but it's good to know about that forces and accelerations are connected. And finally, Newton's third law is one that can explain things like rocket ships. How does a rocket launch away from the Earth? Well, it actually pushes material in one direction that causes the rocket ship to go in the other direction. That's the law of action and reaction forces. Equal and opposite forces act on different bodies that are pushing against each other, that experience force between them. These observations, universal laws of motion in physics that Newton worked out, are pretty amazing because they work throughout the entire universe. And if you become an astrophysicist, you have to learn these very carefully and all of the things that come with them. But we're actually a little bit more interested in what Newton had to say about gravity, the connection between all this motion and the motion of the heavens. Some of the other things that Newton was able to come up with that we eventually will describe in our description of motion are quantities that we say are conserved, things that don't change, even given a large amount of time. One of the most famous quantities that's conserved is energy, but there are other quantities that are conserved as well. And there's one illustrated in this diagram, which is the conservation of angular momentum. Things that are spinning around have a size and a speed of the spinning, and they also have some amount of inertia or mass, material, that causes it to be either difficult or easy to keep it spinning or not spinning. If you combine all of those things together, there's a value called angular momentum, where if you calculate the size, the speed, and the mass of an object and multiply them together, you get a rough estimate of how easy it is for an object to be spinning around and how hard it would be to get it to stop. Objects that are very massive, that are spinning rapidly, and that are large have large angular momentum and continue to spin. And if you change those objects in certain ways, because the quantity of angular momentum is conserved, let's say one of these quantities, either the mass, the size, or the speed of spinning is decreased, to compensate, one of the other things has to increase. And the classic example is the figure skater, who starts off very large, moving very slowly in her spinning around, bringing her arms in, she suddenly spins more quickly. That's because her size has decreased. Her mass has stayed the same, so the only other thing that can increase is the speed of her spin, explained through some of the rules that Newton came up with. So how does Newton explain things like the International Space Station? People that are free falling, for example, the people you see in this diagram here, or this picture here, and that are experiencing weightlessness. Well, Newton explains it in very much the same way that we would explain throwing an object into the air. We call that projectile motion under the influence of gravity. If you look at the motion of these objects in our own solar system, they're following the same trajectories that an object that's thrown close to the Earth follows. Here are the trajectories we see in our own solar system. On the Earth, the trajectories are followed, but they end up getting interrupted because you end up having the ground that gets in the way. If you get to a high enough speed, move above the atmosphere, you can continue to move in these trajectories and are moving fast enough so that the ground doesn't get in the way. In other words, you are missing the Earth as you go around in an orbit over and over again, but you're still under that influence of gravity. You're still falling. All of the objects you see here are still falling around the sun. It's just that they're not close enough to the sun to actually collide with it. So they continue to fall over and over and over again in the form of an orbit. This is what Newton kind of described in his description of how gravity worked. The experiment is something like you stand at a very tall mountain and you try to get a projectile to move in one particular direction. As you get it to move faster and faster and faster, and in Newton's time, the fastest things he could imagine were cannonballs being shot out. They would move further and further away. But since the Earth is round, eventually they would start to move in a circle around the entire planet until it came back to where it started. We call that an orbit. This is the description of how that sort of motion happens. Today, we exploit those orbits in ways that are numerous. This is an image that shows how many satellites are launched by human beings that are now orbiting around the Earth, and there are many thousands of them. All right, we're going to move on to chapter 5 now and think a little bit about how light works. Light is a fascinating topic because we have all experienced it throughout our lives, but perhaps are not as aware of the vast array of phenomena that are connected to light. There are forms of light that you can't see with your eyes. For example, this is a picture of the sun taken in light that's higher energy than the light we see with our eyes. We call it ultraviolet light. Now, in order to show this picture, we have to use false colors. Since our eyes can't see ultraviolet, there's a mapping that has been chosen for the different forms of light that are invisible to our eyes. We've decided to put a code in this image so that different colors you see in this image correspond to different invisible colors that you can't see with your eyes. We're going to be looking at many observations this way throughout this class. Sometimes light is going to be invisible to our eyes, but we'll still want to be able to get the information, and we'll use these false colors to do it. Well, what is light? Light, it turns out, is a wave. And it's a very weird sort of wave. Most waves that you encounter in the world are waves like the one you see in this image here, like a water wave, a motion of energetic material that moves through medium. Light is also a form of energy, but it doesn't actually need a medium to move. It's a form of electromagnetic energy, which means that the phenomena that allows for electricity and magnetism is actually what allows for light. And the electric and magnetic fields are what is waving. And these are things that exist throughout the universe, whether or not there's material, which is sort of a different kind of wave. And the first time you encounter it, when you start to study it, looks very strange. But all of the rules that come with water waves or any other sort of wave you might encounter also apply to light. Some of the things that we look at when we try to examine light are how to measure something called the wavelength of light. We can see what that would look like in a diagram like this, where you look at the disturbances that make up the wave and you see how far apart they are in space. We call that the wavelength. Disturbances are associated with crests and troughs, places where the disturbance is maximally high and maximally low, and light exhibits the same thing. We can also count the frequency of light, the number of waves that come in a given amount of time, let's say a second. And we usually measure that in measurements of hertz, which are waves per second, or sometimes indicated as seconds to the -1. or sometimes indicated as capital H, lowercase z. These are all the same things. We'll do some calculations with waves, especially light waves, to kind of see how those things work. Another phenomena that light has, regardless of what kind it is, but this was first noticed in visible light, is that as you move further away from light, it becomes dimmer and dimmer. But it becomes dimmer in a very particular way. It follows something called the inverse square law. This is illustrated in this diagram. You imagine that's light's coming out from a source, let's say the sun. And as you get further and further away from it, the same amount of light is now passing through bigger and bigger areas, because in order to collect light, you need an area. Well, areas are related to each other if they are centered around the same object by the square of the distance that they are from that object. If you have a ball and then you have a ball that has twice the radius, the area of the ball with twice the radius will be 4 times the area of the smaller ball. As light goes out into the universe, it gets diluted by these concentric spheres. And this is what we see as the inverse square law for light. It's a fascinating effect, but it's not one that's intuitive. Most people have this idea that as I move twice as far away from a light object, the light should become twice as dim. In fact, that's not what will happen. Because of this rule, if I move twice as far away, the light will become 4 times as dim. Or if I move 10 times further away, it will become 100 times as dim. This is an important fact about light in the sky. It's one that we will use quite a bit and comes into our calculations that we'll be using for the class as well. So what are the different forms of light that we have to worry about? Well, there's the visible light that we see, the rainbow spectrum. But on either side, there are 2 forms of light you may have heard of. We already discussed ultraviolet light, which is light that's bluer than blue, who's, let's say, more energetic than the visible light. And then on the other side, there's light called infrared light, which is less energetic than the visible light, redder than red, not visible by our eyes. But some ultraviolet and some infrared light can penetrate our atmosphere. So if we are careful with our instruments, we can see just some kind of the edges. As you go to different parts of what we call the spectrum, the electromagnetic spectrum of light, you will find that some of the light doesn't actually penetrate our atmosphere. Our atmosphere is opaque to those forms of light. And much of the ultraviolet light is opaque to our atmosphere, which is actually a good thing, because that's what protects us from being exposed to some of the harmful ultraviolet radiation. Infrared as well is often blocked by our atmosphere, and that has implications in other places as well. In fact, you'll do a lab next week on the greenhouse effect that's directly caused by that phenomena, that light doesn't travel through our atmosphere very easily when it's infrared light. But you can go to even further parts of our electromagnetic spectrum and investigate them. There are parts of the electromagnetic spectrum which are called microwaves, which are even redder than infrared, or we might say lower energy than infrared light. And then there is at the very lowest forms of energy, and in fact, energy is related to the frequency of light. So we might say at the lowest frequencies of light, we have radio waves. Students are sometimes surprised to find out that radio waves are a form of light, but they are. They're a form of electromagnetic radiation, the same as visible light. They just happen to be much, much lower in frequency or much higher in wavelength. And those radio waves are things that you use all the time in your day-to-day life. You use them for getting information on your phone. We use them when we're using things we actually call radios. We use them for Wi-Fi. We use them all the time. It's a form of light that penetrates everywhere in our lives. But we can also talk about higher energy forms of light, X-rays and gamma rays, which are even more extreme than the ultraviolet. Now, except for radio and visible light, all of these different forms of light can't really penetrate our atmosphere. So if you want to take pictures of the sky and these other forms of light, you really have to go to space. You have to send a space telescope up. But if you are interested in radio or you're interested in optical light, visible light, you can put a telescope here on Earth. We tend to put the visible light telescopes high on mountaintops. We tend to put the radio telescopes low down in valleys where they can kind of collect more of the radio. So let's say you launched a telescope that was sensitive to the X-rays and looked at the sky. What might you see? Well, this is what you would see. It actually looks very different than the sky we see with the visible light. This is a map that was made of the entire sky in X-rays by a satellite that flew about 40 years ago. How is light made? It's a pretty good question. Well, there's different ways that light is produced. Generally, you have to have something that has electricity and magnetism involved in it. But almost all matter has electricity and magnetism. And different processes that can excite those electric and magnetic fields in matter can exist. And one process that can excite those electric and magnetic fields is heat, or the increase of temperature of an object. Any object in the universe that has a temperature is going to emit light. And it will emit light in a very particular way. It will start at very low temperatures to emit very low frequency light. That's the radio and the microwave and the infrared. We, as human beings, exist at fairly low temperatures. It might feel like a hot day, but ultimately that's not a very high temperature, not high enough to produce a lot of the light that we can see with our eyes. So if we were to ask what sort of light is the matter in this room creating, it's creating light that's in the infrared part of the spectrum, which is how night vision goggles work. Even though you don't see visible light reflecting around you, you can put on a night vision goggle and see the emitting light from the temperature of different objects that are around you. Once you get to about 3,000 degrees Kelvin, and we're going to use the Kelvin scale in this class, which relates to the Celsius scale by a subtraction of about 300 or so. Then you will start to see visible light showing up. And you may have seen this if you've ever looked at an electric stove that has started to turn red. That red is actually being emitted by the temperature of that stove as it gets to 1,000 degrees. Now, of course, you're not heating up your object to 1,000 degrees necessarily, but the heating element right there in the middle is, and that's what we see as that incandescent reddish color. As we get to higher and higher temperatures, we end up seeing more and more colors. The frequency of light goes from being very low at the reddest colors to being high at the bluest colors. And you can actually calculate what that frequency of light is by using a simple formula, which is discussed in your text and you'll use in the problem set. But the thing that we need to understand is that as we get to hotter and hotter temperatures, the light is going to become bluer and bluer and bluer. So we start off with very red light. When we get to temperatures that are roughly that of the sun, at about, let's say, 6,000 Kelvin or so, which is about the temperature of our sun, we get almost all of the lights in fairly equal proportion. That means that we experience all the colors at once, and we perceive that as white light. If you get to hotter temperatures than that, let's say 10,000 Kelvin, then you end up with a lot more of the blue end of the spectrum, and the light will appear almost bluish. When you look out into the night sky, you see two different types of stars. You see red stars and you see blue stars. The red stars don't look ruby red. They might look orangish. The blue stars don't look like a deep aquamarine. They might look like a brilliant white with a bluish tinge. But that's the division that astronomers see. That division between red stars and blue stars is actually a division in temperature. This is one of the ways we can tell how hot stars are. It's an important way for us to describe something. And because we know exactly how matter behaves and how it emits those forms of light at different temperatures, that's enough information for us to calculate quite a bit about stars. We're going to figure out that that lets us know the size of stars, the distances to stars, the temperature of stars, and even eventually what stars are made of. When I said that white light is the combination of all the colors of light, this was something that was really explained well by Isaac Newton, who used a prism to show this. You take a prism, which is just a cut piece of glass at an angle, and allow white light to shine through it. Different wavelengths of light will travel through it at different rates. And so that actually causes the white light to spread out in its spectrum. And you'll see red on one end and violet on the other. They've actually indicated the wavelength of those light. Red light has a wavelength of about 760 nanometers. That's a billionth of a meter. And violet light has a wavelength of about 380 nanometers, or 380 billionths of a meter. You can go to even higher and lower wavelengths than that, but of course they're not visible to the human eye. So this is what we have for our consideration. We've got the spectrum of light in nanometers, going from a little bit more than 400 to maybe a little bit more than 700. And then, of course, on either side, there's the invisible part of the spectrum, the ultraviolet and the infrared. I can expand all of that as well. But I can also look at what light looks like when I'm coming from the sun, for example. If I took the sun and passed it through a prism, I get what you see here. You get all the different colors of light at different intensities. But you also see these dark bands. These were mysterious for probably about 100 years, maybe more like 75 years after they were discovered. It was only later that people began to realize that this was due to atoms that were in the atmosphere of the sun that were absorbing very particular wavelengths of light for reasons that took us quite a while to figure out exactly what was going on. It was a pretty remarkable discovery that atoms will absorb and emit light in very specific ways. In fact, they don't emit all of the light, unlike something that has just a temperature, but an excited atom will only emit very particular wavelengths or frequencies of light. We call those the photons of light. This is because atoms have very particular energies at the atomic level. Each electron can only be at a particular energy inside the atom. And as it moves from one energy to another, it emits one kind of light, one particular photon, and we see those as lines. In here, they're indicated as emission lines or emission spectra. At the very top, you see a continuous spectra. This is what you would get if you had some material that was opaque, that you couldn't see through, that had a very particular temperature. You would see all the colors of light in the arrangement that we had described before, redder for colder objects, bluer for hotter objects. Very cold objects like you and I would be in the infrared. Very hot objects might have a lot more ultraviolet light, for example. But if you just have individual atoms that the light is passing through, or that are being created by individual atoms, and when you talk about individual atoms, the sense of temperature disappears. You don't really have a temperature for an individual atom. Temperature is the average movement of lots and lots of atoms. For individual atoms, only very particular wavelengths of light are produced. And here are some examples of what that looks like. These are called emission spectra. These are some things you'll be working with in the labs next week. Now, how do we know what atoms are? Well, this was actually an interesting thing to work out. It took many, many years to do so. The experiment that did it looks like this. What they did was they took some material that they could get very, very thin sheets of and fired particles at that material and found that most of the material was empty space. Even though there were atoms in it, most particles could sail right through the atoms. And that empty space indicated that there were two parts to an atom. There were the parts of the atom where the electrons were on the outside, negatively charged particles. And then there was something called the nucleus on the inside, which had positively charged, and we eventually discovered also neutral particles called neutrons and protons, the protons being positively charged, the neutrons being neutral. So this is a simple model of an atom. You've got an electron, you've got a proton, and the proton's at the center. It's very dense, it's very small. The electron kind of surrounds it in a big cloud, but most of it is empty space. The simplest atom is a hydrogen atom. Here's a little bit more complicated atom called a helium atom. This is the next most common atom in the universe after hydrogen. 2 protons, 2 neutrons, and 2 electrons. The protons and neutrons are at the center of this atom. And you can see the atom is very small, 10 to the minus 10 meters, very tiny thing. Now, you can also change the characteristic of the nucleus. And if you keep the same number of protons, but change the number of neutrons in a nucleus, you end up with something called an isotope of an atom. Here's some of the more famous isotopes of hydrogen. We'll actually be referring to isotopes later in the class, because some of these particular kinds of nuclei are going to be important for our understanding of the origin of lots of the objects in our universe. All right, so what does this have to do with light? Well, if we have atoms and then we have electrons, the electrons can be at these different levels. They usually indicate these levels by the letter N. So the lowest level is called N equals 1, and the highest level, well, it can go up very, very high. As electrons transition between different levels in the atom, this movement is a little bit hard to describe. It's not something you can see with your eyes. Atoms are particularly tiny. This can't be seen, but we can see the effects. So this is the model that we have as we're describing this. As an electron goes from one level to another level, it loses energy if it goes from a high energy level to a low energy level, and then will emit that energy in the form of one type of energy, light. We call that a photon. That photon gets emitted with a very particular frequency. It's a high energy photon. It will be emitted with a high energy frequency and a high frequency light photon, and that might be something like violet. If it's only losing a little bit of energy, it might emit something like a red photon. A red spectral line is what we see here. This is really the description, or one of the simpler descriptions we have for models for how light is produced by atoms. It's something that you'll be dealing with when you start to think about our observations of the sky, because we see this sort of thing when we point our telescopes and put prisms at the end of them and look at the spectrum of objects coming from different parts of the sky. So this is the same explanation, just in much more detail. For hydrogen, there's well-known series of lines that you can see. And the ones that are visible to the human eye are the Balmer lines, but there are also lines that are ultraviolet, and there are lines in the infrared as well, but you need special instruments to see. So how does this relate to astronomy? Well, let's imagine that I have some opaque ball of material that's very hot. Usually we call it a star. That star is going to produce a continuous spectrum because of its temperature. And we might be able to see that spectrum using our telescopes. But everywhere in the universe also has clouds of gas, individual atoms that might be getting in the way. And if those individual atoms get in the way, they can absorb some of the light of that star, but they'll only absorb the light for the particular energy that those electrons can absorb. And you see that as the dark line. So that explains why the sun had those dark lines in its spectrum. It's because that energy was being absorbed by particular atoms in the sun spectrum. And other times, you might be looking just at a cloud of gas that doesn't have any bright, hot, opaque star behind it. And in that case, you'll just see individual lines, as you might see down on the lower right, something called the bright line spectrum, or I would call an emission spectrum. And emission spectra are seen in places where we see clouds of gas and dust in our galaxy, places we call nebulae. All of these observations are seen out in the sky, out in our astronomical world. And we're going to be using these observations to learn more about the objects that we can't visit directly, but we can measure from here on Earth and get some really interesting information about. There's one last phenomenon we should discuss about if we're going to be interested in light, and that is because light is a wave, the frequency and wavelength of light can be affected by the movement of whatever's producing the light. If the object that's producing light is moving towards you, then even though it might be producing some light that's very low frequency, that frequency will be enhanced, it will be kind of boosted up because of the object's motion towards you. And if it's moving away from you, the reverse happens. The frequency gets pulled down. This is something that you've probably experienced in your life not with light, but with another type of wave, sound waves. Sound waves, when an object is moving towards you, will sound higher pitched. And when it's moving away from you, will sound lower pitched. This is something that wasn't known about when the phenomenon was first described, because things didn't move as quickly as they do today. But now we hear this all the time with traffic, with cars, with trains, anything that's moving quickly. We can actually hear the high pitch as it comes towards us, the low pitch as it goes away. Well, objects that have light being produced by them will do the same thing. The relationship is between the speed of the wave and the speed of the object. And the closer those two things are to each other, the more prominent this phenomenon is. It's called the Doppler effect. So for the speed of sound, you have to be moving pretty quickly to hear this effect. But since sound moves at about, well, 1 kilometer every 3 seconds or so, that's very fast, but it's not so incredibly fast that it's impossible for us to reach it. With light, that's a different matter. We don't create objects that move close to the speed of light at all. So we don't often see the Doppler effect with light, but we do out in space. We do with astronomical objects, which can be moving at those high clips. In those cases, the light's frequency will change, which means the colors of various forms of light will change. An object that starts off moving towards us will see its light shift towards the blue, and we call that a blue shift. Whereas if it's moving away from us, it'll shift towards the red, and we'll call it a red shift. This is something we can directly calculate, and we will, based on knowing the speed of light and doing some simple manipulations with the speed relationships. We can actually see how much that shift will be. In general, these shifts are so tiny that you need special instruments to study them and really identify that they're there. But the fact that they are there gives us some incredibly important information about how things are moving around in our universe. All right, we're going to move on to chapter 6 and talk a little bit about how telescopes work and what we can do with telescopes. Here's perhaps the most famous telescope ever, the Hubble Space Telescope. It has been giving us great information for 30 years now and continues to be a great telescope. It's an optical telescope and was used as an optical telescope in space to avoid some of the effects of the atmosphere. And it has given us some beautiful images. But we can also use telescopes to look in different wavelengths as well. We don't have to just look with visible light. So here we've got the same constellation, the constellation Orion, which by the end of this course, if you were to go out in the evening, you could go out and check and look at Orion. We can see it in visible light, we can see it in X-ray light, and then we can see it in infrared light. And it looks very different depending on how you look at it. There are fascinating things to observe in each forms of these lights. And they are why we need different telescopes. For the visible light telescopes, we can use telescopes on Earth. For X-rays, we have to go to space. For some infrared, we can get information on Earth, but often we have to go to space for infrared as well, as with the famous James Webb Space Telescope, which is an infrared telescope. So when telescopes were first invented, there were 2 types, and they were only for optical light. The 2 types were the refracting telescope, which is what most people have in mind when they think of telescopes. But most telescopes these days that are used for science are actually reflecting telescopes. Refracting telescopes use lenses. Reflecting telescopes use mirrors. It's much easier to build a big mirror than it is to build a big lens. And there are various ways you can build telescopes. This shows you 2 different ways that you can do it, but you can get to very, very large telescopes with very big mirrors. This is one for the Very Large Telescope in Chile. That's actually the name of the telescope. 8 meters in diameter. At the time this telescope was built, it was the biggest telescope in the world. Here are some other large modern reflecting telescopes. You can get a sense for how big these things are. There's actually a person in the left-hand side at the bottom of the telescope. Amazingly gigantic instruments. You need a big mirror in order to collect very dim light, right? Because area is what allows us to collect light. It's also a good idea to build your telescopes at high and dry sites. That way you're going to get the best views, the clearest views, the least amount of weather that's going to cause problems. There are ways of even getting around some of the more problematic aspects of the atmosphere. Atmospheres blur your images. They cause that twinkling of starlight that's due to kind of small little changes in the atmosphere. But if you shine a laser in the same direction that you're looking, you can actually use your telescope and look at that laser and make tiny adjustments depending on how that laser is moving to your telescope that allows you to adjust and see much more accurately what that light from a distant object is doing. That's called adaptive optics. And that gets used in telescopes around the world these days to make some incredible images. This is an image of the planet Jupiter using adaptive optics. We collect most of the information these days on a computer using something called the Charged Coupled Device, a CCD. This is an electronic device that when it's exposed to light can actually count how much light it's been exposed to. And that's how we produce all of the astronomical images you see. And that technology has been imported into your phone. This is what allows you to have a small little digital telephone that takes pictures. That's where your camera on your phone comes from. Some telescopes are sensitive in other wavelengths. Infrared's a famous example here. I think this is a great image here to demonstrate that infrared's sensitive to different things than visible light. One side we see the visible light, and one to the other side we see the infrared, and you can see through different things in infrared, and there's different things that show up more prominently in infrared than they do in visible. You can try to figure out why certain things look bright in the infrared or dark in the infrared, and vice versa. You could also build radio telescopes. This is the first one ever built. This was doesn't look much like a telescope, but it's really just a number of radio receivers that was pointed towards the sky to try to detect things in the sky. And this was the one that detected the Milky Way, which has a very bright source of radio waves. Today, we can use radio telescopes, analyze the data, and then use false color to really get a sense of what's going on. This is a famous image of a galaxy called Cygnus A. And the different colors you see are different intensities of radio waves coming from a galaxy that's absolutely enormous. Here's a very famous radio telescope called the Green Bank Telescope in West Virginia. It's now the biggest telescope, single dish telescope that exists in our country. You can also do radio astronomy with arrays of telescopes and put all the information together using something called interferometry. Here's one of the more famous arrays called the Atacama Large Millimeter Array, called ALMA. There are also arrays that extend over the entire planet, putting together radio information in simultaneous observations to get very detailed look at things like the center of our galaxy. And there was a famous image that was made at the center of both a nearby galaxy and our own galaxy that got very close to discovering the very edges of what's going on in there towards something called a supermassive black hole, which we'll discuss later in the class. And there are also very large telescope dishes that you would build that would be sort of semi-permanent. The biggest one in the US used to be the Arecibo telescope in Puerto Rico, but unfortunately it was destroyed in 2020, and it doesn't look like it's going to be rebuilt, which is a shame. But it was a very important telescope for many years. If you want to observe certain wavelengths of light, you have to get above the atmosphere. So one idea was to fly an airplane that would go high enough. And for about 20 years, this observatory, SOFIA, was taking images and data from in the infrared from an airplane. It just flew its last flight a few months ago. And so this is no longer a telescope that is used like this, but there have been some amazing discoveries made with this particular telescope. Here are some observations from an infrared space telescope of different things. Remember, these are false color images. So you shouldn't be misled to think that, these telescopes are seeing these colors of blue and red and gold in the sky. They are seeing definitely light, and the light is arranged in this fashion, but we have to choose the color pattern, the palette ourselves, kind of like an Instagram filter. If you allow yourself enough time, you can see very dim and very distant objects. The dimmer the object, the harder it is to see, the longer you need to kind of sit on the same patch of sky and collect that information. Here's a famous image that was collected by the Hubble Space Telescope, the Hubble Deep Field. This is an enormous array of galaxies that are very dim. And the reason that they're dim is that they're very, very far away. And so this is some of the most distant objects that we're seeing. But another way of thinking of it is it's some of the dimmest objects we're seeing. Here's another telescope that's still in operation, has been for nearly 40 years now. This is the Chandra X-ray telescope. It was launched, I guess it's really only been 20 years. It was launched in 1999 and is continuing to give us information about the X-rays out in space. And of course, we now have a new space telescope that's sensitive to the infrared called the James Webb Space Telescope. We'll be looking at some of their images over the course of the class. There will always be new telescopes that people will want. One of the ones that is proposed to be built is one that should be 40 meters across, absolutely enormous in terms of the size of the mirror. This is called the Extremely Large Telescope, which is much bigger than the Very Large Telescope in Chile. So that's my exploration of chapters 3, 5, and 6. I'll soon be adding a walkthrough for problem set 2 so that you can get a sense for how to do some calculations and think about some of these concepts that are in the chapters. I want you to keep reading these chapters and really learning about these things, however, because this is all often very new information. It can come in a big flood. And so we're going to try to get a grounding, but then we're going to quickly move on and try to see what we can learn from understanding gravity, light, and how we actually measure these things. So thanks for joining me. I hope you learned a little bit, and we'll see you very soon.